Hey y'all, so in the next little bit, I'm going to be going over with you the most commonly missed questions from our Gold Quest activity in class today. Now the Gold Quest activity went over kinematics, dynamics, and circular motion. All of these were questions from the AP website, so they're AP style, AP level, and so I wanted to go over the ones that we missed more than 40% of. Okay, now that doesn't mean you missed it. It just means as a class, of the students that got to these questions, at least 40% of the students missed it. And some of these questions, the ones near the end, every single student that tried the question missed it. All right, so we're going to start a little bit easier, and as we get through, we will get to more challenging questions. All right, so again, we're going to get through as many of these as we can. The reason why I chose 40% is because that's usually about the mark that differentiates a 2 from a 3. And so for most of you, that is the minimum goal, is to make sure that we get a 3 on that AP exam. Now, to be fair, there were questions that everybody that answered that question got it correct. Okay, there were about 15 out of the 60 questions that as a class, we would have got a 5 on. Okay, but there's about 20 that as a class, we would have failed. So those are the ones we're going to go over right now. All right, so here we go. We got a block projected up a frictionless plane with an initial speed v. The plane is inclined 30 degrees above the horizontal. What is the approximate acceleration of the block at the instant that it reaches its highest point on the inclined plane? All right, so in order to do this, it's probably a good idea for us to draw a picture. So we do have an inclined plane that is at 30 degrees, right? It does say it has an initial speed v, so it has some initial speed v at the bottom, and we are looking for the acceleration of the block at its highest point. Now, the first thing we need to ask ourselves is, what type of physics do we want to use here? Now, the things that come to my mind initially are kinematics, dynamics, and energy. All right? Now, as I think about kinematics, I'm thinking, well, I don't really have anything other than the initial speed v, and I don't even know what that is, right? And so I'm not sure that kinematics is the best. In addition, in order to do kinematics, we usually need that acceleration. I don't really have any other information, probably not kinematics. I'm thinking energy. I could do something with energy, and perhaps that's the way to do it. But if I think about energy, I'm like, actually with energy, energy doesn't have acceleration in it at all. So that's actually not very helpful to calculate acceleration. So my final thing is, okay, well, it's probably going to be forces then. Now, forces makes a lot of sense, because we know that the sum of the forces is equal to ma, or as it's stated in your formula packet, acceleration equals the net force over the mass, which is just a rearrangement of this. But most people know this best as sum of the forces equals ma. So really, if I want to know the acceleration at the instant it reaches its highest point, all I need to do is look at the forces on my block at that point. All right? So what I have here is I have the force of gravity, which is downwards, and then I've got the normal force, which is upwards. Now it says it's frictionless, so I don't have friction. At the highest point, it's at rest. So it really doesn't matter. I'm not even going to need this v here. All that I need to do is I need to look at the sum of the forces and figure out what I get. Now, please remember that when we're on a ramp, it's usually very, very helpful to slant the ramp. Now, one of the reasons we do this is because we want our acceleration to be on one of those axes. And as the block goes up the ramp and stops and then comes down the ramp, the acceleration is always going to be parallel to the ramp. So it would be really, really nice if it's horizontal there, right? Now, as I work through that, I recognize, well, it's not accelerating up and down off the ramp. It's just going parallel to the ramp, which means that my normal force and the vertical force of gravity are going to have to balance out. All right? Then all I'm going to have here is the horizontal force of gravity. That is the only force that's going to be necessary in order to be able to answer this question. So for that force, I know that Fg is equal to mg. I know that this angle right here is that 30 degrees. Remember, the force of gravity was here. I've taken the axis and rotated it 30 degrees so that it matches my ramp. And so therefore it's rotated through 30 degrees. That's 30 degrees right there. And so I can say I want this, which is opposite my 30. So I'm going to go sine of 30 is equal to the opposite, which is the FGX, the horizontal component of my force of gravity, over the hypotenuse, which is the force of gravity. Now, you may be saying, but I don't know the mass. It's okay, remember? A lot of times when we're working with these variable manipulation things, we just work through it, and a lot of times those things are going to disappear, which is what we're going to see right here. So I multiply both sides by FG. We already said FG is mg, so that's going to be mg sine theta, or sine 30, sorry, I do have the angle, is equal to that horizontal force. Now, why is that important? Because that is the net force. All the other forces balance out. And so that horizontal force right here is going to become the net force, the sum of the forces. And so my final answer is going to be m times g sine 30 will be equal to ma. And as I mentioned before, you'll notice I divide both sides by m. Don't just start crossing stuff out. Divide this side by m. Divide that side by m. We see they both cancel out. And so we just have g sine of 30. Now, sine of 30, you can punch that into your calculator, or you can figure it out from geometry or algebra 2 trig or wherever you learned your trig stuff, and you'll recognize that the sine of 30 is equal to 1/2. And so when I do g times 1/2, g is 9.8, which is approximately 10. And so half of 10 is approximately 5 meters per second squared, which is then equal to the acceleration of the block. Do not forget that even though at its maximum point it is at rest, it is not at rest for a period of time. It's just that instant after which any amount of time, even if you look at a billionth of a second later, it's already moving. It has accelerated. The acceleration is constant the whole time it goes up the ramp and the whole time it moves down the ramp, as long as it's frictionless there. All right? So that is our first question. Let's move on to our second one. So in our second question, we have 3 forces that are acting on an object. If the object is in translational equilibrium, which of the following must be true? So translational equilibrium, this lets you know that we're not looking at rotation. It's just horizontal equilibrium. Now, horizontal equilibrium just means that it's maintaining its state of motion, that its velocity is staying constant. It's not accelerating. In order for it to not accelerate, the forces must be balanced. That's all that we know. So let's go ahead and read through the possible answers and see if we can figure out what's going on. The vector sum of the 3 forces must equal 0. Yeah, that's basically what I just said, right? Vector sum means that you're paying attention to the directions, that as you add those directions together, you end up getting 0. If the vector sum of the forces is 0, then according to F equals ma, your acceleration will be 0, and we will be in translational equilibrium. Number 2. So number 1, yeah, I'm okay with that. Number 2, the magnitudes of the 3 forces must be equal. Absolutely not, right? And I can show you an example of why that would not work. I could have a force of 5 newtons this way, a force of 2 newtons that way, and a force of 3 newtons that way. Those would all balance out and give me that translational equilibrium. However, those 3 are not equal. So number 2 must not be true. It doesn't have to be true. It could be true, but it doesn't have to be true. Number 3, all 3 forces must be parallel. All right, well, according to the drawing I just made, yeah, they would have to be parallel. However, you could change those forces slightly so that you have something like this, where these vertical pieces cancel each other out, and then the horizontal pieces cancel out with the 5 newtons there. So do they have to be parallel? Absolutely not. So the answer to this one, the vector sum of the 3 forces must equal 0. That is the only thing that must be true. Okay, please make sure that you pay attention to those modifiers there. Must be true, could be true, are not true, right? Must be true, only number 1. All right, Next, we got a block moving to the right on a surface, on a level surface, with friction is pulled by an increasing horizontal force, also directed to the right. As the applied force increases, which of the following is true of the normal force and the frictional force on the block? Okay, so it's already moving to the right. Why is that significant? Well, if it's already moving to the right, it means that it already has a specific type of friction. It already has kinetic friction. Now, if it already has kinetic friction, then that means that it's already going to be sliding. Remember, we talked about kinetic friction, and kinetic friction does not change based off of your speed. We tried this in the lab. We did it in the lab when we showed that pulling it faster, pulling it with a stronger force, that did not affect the amount of friction that there was, right? You could pull it faster, and as long as you maintain that speed, we ended up having the same friction there, okay? Didn't matter how fast or slow it was, all right? So first things first, how would it affect the normal force? Well, obviously it wouldn't affect the normal force. The normal force is a perpendicular force that has nothing to do with a horizontal force. A vertical and horizontal are always independent of each other. So therefore, normal force ain't going to change. How about the frictional force? Well, we just talked about the fact that if we already have kinetic friction, then changing that increasing horizontal force does not change the amount of friction. Remember as well, we do have the equation from our formula packet, which is that the force of friction is equal to the coefficient times the normal force, right? Absolute value bars and all that kind of stuff. But the force of friction only depends on the coefficient and the normal force. And if the normal force is independent because it's vertical and we're moving horizontal and the force is horizontal, right? This additional force is horizontal. That's independent. That's not going to change. The coefficient only depends on the two surfaces. So if the coefficient doesn't change and the normal force doesn't change, then the frictional force cannot change either. And so therefore, the answer is that neither of them will change. They must both be constant. All right? All right. Two blocks of masses, 1 kilogram and 2 kilogram, respectively, are pushed by a constant applied force across a horizontal frictionless table with constant acceleration, such that the blocks remain in contact with each other as shown above. 1 kg block pushes a 2 kg block with a force of 2 newtons. The acceleration of the two blocks is, all right, well, let's think about it. We have the 1 kilogram block pushing the 2 kilogram block with a force of 2 newtons. So if I look just at the 2 kilogram block, then what are the forces on it? You've got gravity pulling down. You've got the normal force pushing up, and then you have the force of block 1 pushing to the right. Those are the only forces, right? Remember, this does not push on that. Only the things in contact with block 2 will exert a force on it. Because it's frictionless, those are the only 3 forces. Because we know that this is 2 newtons, we should then, knowing that these two cancel out because it's not accelerating up and down, we should then just be able to use our sum of the forces equals ma to then determine the acceleration of the 2 kilogram block. So the sum of the forces is 2 newtons. The other two cancel out, so I'm just going to put 2 there, equals the mass, which is 2 kilograms, times the acceleration. We solve for acceleration. We get the acceleration as 1 meter per second squared. And you may say, well, that's all real nice, Mr. Bywater, but it asks for the acceleration of the 2 blocks. Well, guess what, y'all? They are stuck together. If they are stuck together, their acceleration is the same. Whatever acceleration is of 2 will be the acceleration of 1 as well. So therefore, our answer is that the acceleration of the block is 1 meter per second squared. That's it. Next question. The system shown above, to the left, is released from rest. If friction is negligible, the acceleration of the 4 kilogram block sliding on the table shown above is most nearly. So we are trying to find the acceleration of this guy right here. All right? Now, it is frictionless. It's a good idea if we want to be able to solve for the acceleration of the 4 kilogram object. You may say, well, let's do the forces on the 4 kilogram object, kind of like we did in the last question, right? So we do the force of gravity, we do the normal force. Those two, of course, have to be equal. They're going to cancel out. Then we have the tension right here. Now, I don't know what the tension is. Without knowing the tension, I cannot then solve for the acceleration. So we can't do that, right? And so we say, well, what about the other one? We know the force of gravity on this one and tension on that one. Well, can we figure out tension there? The answer, sadly, is no. Okay? Do not be confused. A lot of students will say, well, aren't these equal? Not once it's accelerating. Once it is accelerating, in order for it to accelerate downwards, even the instant that you release, it already starts that acceleration. And therefore, in order to accelerate downwards, the downward force must be greater than the upward force. Now, hopefully what you're thinking is, well, it said the system. Yeah. Remember, when we have things connected by a string, very often the easiest way to think about these questions is by looking at the system. So if we look at the entire system, including the 4 kilogram and the 2 kilogram, you'll notice that tension is now internal to the system. Because the tension is internal to the system, we don't have to look at it. All we have to look at are the other forces that are acting on it. Okay, we've got the force of gravity down on the 4 and the force of the normal up, but those two, again, they cancel out. Number one, they cancel out. Number two, they're not in the direction of the acceleration. They're perpendicular to it, so they really don't matter anyway. So the only force that's going to matter here is the force of gravity on the 2 kilogram block. So when I do my sum of the forces equals ma, the sum of the forces is just the force of gravity on the 2 kilogram object. So that would be mg, where the mass is 2 and g is 9.8. Once you've done that, you can then put the mass here, but remember the mass that we're talking about is the mass of the system, which will be the total 6 kg, then times the acceleration. From there, you should be able to plug those numbers into a calculator. Now, when I use my super fancy calculator to solve this, I do get 3.2666666. Now, 3.26, it looks like I only have 2 significant figures here, so I'm going to write my final answer as the acceleration is 3.3 meters per second squared. Just like that, all right? Okay, we are doing pretty good right now. Let's go ahead and move on to the next question. All right, now we've got a planet with half Earth's mass and half Earth's radius is discovered. What would an astronaut who weighs 800 newtons on Earth weigh on that planet? All right, so our first goal needs to be, how does changing the mass and changing the radius affect the force on an object? All right, so we know that Newton's law of gravitation is the force of gravity equals G m1 m2 over r squared. All right. Now it does say that the planet has half of Earth's mass. Okay, so this is going to be 1/2. And then it says that it has half of Earth's radius. So this number down here is going to be 1/2 as well. Okay? Everything else is going to stay the same. The G is a universal constant. That stays the same. The mass of the astronaut stays the same. So that doesn't change. So at this point, I'm just going to look at these two things. Now, halving the mass would half the force of gravity. They have a linear relationship. So that means I'm going to have half because of that. Now here, I've got half of the radius. Now that half is going to be squared. Now normally, if I do half of the radius, then that would end up doubling the force of gravity. But because it's squared, 1/2 squared is 1/4. And dividing by 1/4, is the same thing as multiplying by the reciprocal, which is times 4. So halving the mass is going to half the force. That should make sense. Less mass, less force. And then halving the radius is going to quadruple the force. And that should make sense again. The closer you are to an object, the stronger that the force is. So we put those two things together. We say, well, this one was half, that one was 4. That means overall now my force should double. So if he weighed 800 newtons on Earth, he will now weigh double that, or 1,600 newtons on this new planet. Now, if the question was, what will his mass be? Well, in that case, you would just take that 800 newtons, which is the force of gravity. You'd say 800 equals mg. You would divide by the g of the Earth. You would get his mass. His mass would not change as he goes to a different planet. Okay, so again, be careful about the details. Make sure you're paying attention to what's there. The weight would change. He would be twice as heavy, 1,600 newtons. The mass would not. The mass, again, will approximately be about 80 kilograms. All right? Okay, moving along. A ball of mass m is attached to a vertical rod by 2 massless strings. The rod is rotated about its axis so that both strings are taut. Okay, so a rod here, 2 strings. You're rotating the rod so that the ball is swinging around and both of these strings are tight. Okay, there's no looseness there, there's no sagging, none of that. Okay, with tensions T1 and T2. The strings and rod from the right triangle shown in the figure above. To the left, you get what I'm talking about. The ball rotates in a horizontal circle of radius r with a speed v. What is the magnitude of the net force on the ball? Well, this is one of those questions where the whole purpose of this is, do you really get it? Do you really understand that when an object goes in a circle, that the net force is the centripetal force? It doesn't matter what tension 1 is. It doesn't matter what tension 2 is. It really doesn't matter what the force of gravity is. None of that matters. If the object is going in a circle, then the net force is the centripetal force. Now, that is the combination of all of your horizontal forces. The vertical forces, yeah, they're going to balance out. They don't matter. The horizontal forces, the horizontal component of T2 and the horizontal component of T1, those should add together to give us the centripetal force. But that's not necessary here because we know that the centripetal force is mv squared over r, right? They give us the mass of m, they give us the speed of v, and they give us the radius of r. Therefore, what is the magnitude of the net force? Well, y'all, it is mv squared over r, right? In case you didn't remember, we have the centripetal acceleration, which is v squared over r. Force is mass times acceleration, so you take the centripetal acceleration multiplied by mass, you get mv squared over r. All right, that's it. That's all they wanted you to do. It was simply just, do you understand that when an object is going in a circle, that the net force must be the centripetal force? If it's not going in a circle, then yeah, you got other things to worry about. But any circle, then the total sum of the forces have to add together to give you centripetal force. That's all. That's all. Okay, moving on. An object starts from rest and slides with negligible friction down an air track tipped at an angle of theta from the horizontal. A student records values of the object's position along the track at various times. The value of theta can be best determined from which of the following? This is very, very similar to one of the questions that we did earlier, okay, thinking about the block on the ramp. With the block on the ramp, I was able to connect the angle to the force. Let me remind you. So if we have a track with an angle of theta, okay, we have the object which is going to be moving, accelerating down the track. We already know that's going to be the case. They said negligible friction because it's an air track. Okay, so it's going to be able to slide down with very little friction. Why is it sliding down? Well, in order to find out why is it sliding down, then you take the force of gravity and the normal force. And we recognize again, remember, that the vertical part of gravity is going to balance out with the normal force. Sorry, this is not a force here. This is the acceleration, which is that way. And then, therefore, the acceleration is going to then be connected to the force of gravity, right? The horizontal component of gravity is the only thing causing the acceleration there. And so we will be able to go sum of the forces, which is the horizontal component of gravity, is equal to the mass times the acceleration. You may say, but I'm supposed to be finding theta. All right, well, okay, but this is the background, right? If we can find the acceleration, which we can, right? We have distances, we have times, right? Values of an object's position at various times. We get distance, we get time. With that information, we can get speed, we can get acceleration, we can use our kinematics. So we can somehow use our kinematics to get acceleration. Once we have calculated the acceleration, then notice that the FGX, the horizontal component of gravity, is going to be equal to, remember this theta is that theta right there. That is the opposite. So this is going to be mg opposite sine theta. Mg sine theta is going to be this side right here, the opposite over the hypotenuse. The hypotenuse is the force of gravity, which is mg. Remember that your right angle needs to be, I am going a little quicker through this because we already did the setup for this, but remember we got the horizontal, we've got the vertical, and then the angle should always be perpendicular between those two. With this, if we know the acceleration, which we can get through kinematics, then masses cancel out, we know g, and therefore we can solve for theta. All right? Now, if we wanted to go deeper, what would we have to graph? What would we have to graph in order to get this? Well, what are we measuring? We're measuring velocity. We're measuring time. So if we wanted to go deeper into this, okay, well, which kinematics equation would I use? Well, it seems like I would want to use something that has position and time in it. That would be our first one. So that would be our x equals x naught plus v naught t plus 1/2 a t squared. All right? So x naught is 0. V naught is 0 because it's starting at rest. That's given to me. And so therefore x equals 1/2 a t squared, which means that a is equal to 2x over t squared, right? I multiply by 2, divide by the t squared, that would be a. So I can put that in for a here. So now what I have is g sine theta is equal to 2x over t squared. Now, if I'm going to put this into a graph and I want to linearize it, then I need my two variables, the position and the time, to be on opposite sides. I need those to be my x and my y. And so I'm going to go ahead and move the 2 over. I'm going to move the t squared over, right? And so I'm going to end up getting this equation. I'm going to have 1/2 g sine theta, and that will be multiplied by the t squared, which is then going to be equal to my x. Notice that I divided by the 2, or multiplied by 1/2. I multiplied by the t squared, and that gives me this right here. Now you may say, well, that looks really ugly. Yeah, it is pretty ugly, but this is y equals mx plus b. There is no y-intercept. The x is t squared, and the y is x. If I put a graph that has x on the y-axis and t squared on the x-axis, then I will get a straight line And the straight line will have a slope that is equal to 1/2 g sine theta. Holy smokes, by getting the slope of that line, I can put it in, I can solve for, because I know 1/2, I know g, I can solve for theta, right? And you may not have had to do that in this multiple choice question, but my point is this would be an amazing free response question, right? They could give you a free response question, say, well, we're measuring distance and time. What quantities would you need to graph in order to create a linear graph that would allow us to calculate the angle? And this would be it. We'd put x and t squared, and we'd be able to solve for the angle by making the slope be equal to 1/2 g sine theta. All right? So, please remember, summary. We're going to summarize what we just talked about. Number one, we said, how would we get theta? Well, we would get theta by using kinematics with the position and the time. By using kinematics with position and time, we would know the acceleration, which would then allow us to calculate theta. Now, you could do that simply with several different data points, calculate different thetas, average them, and get, an average answer. That would be an acceptable way to do this. A better way to do this would be to actually, with the kinematics, put your x and t in there. Those are my two variables. Rearrange it into y equals mx plus b form, where I have one variable on one side, one variable on the other side. Once I have that, my y will be the x, the distance. My x will be the t squared, and whatever's left, including the theta, is going to be my slope. Snazzy. Snazzy. We get a straight line, and we can solve for theta. That is a great question. Simple, fairly straightforward multiple choice based off of what we already knew. Not necessarily simple, but straightforward based off of what we talked about before. However, it would make a great free response question in those experimental designs. One that's a little bit more challenging than some of the ones that we've seen before. All right? Okay. Next up. Next up. A box of mass m is on a rough inclined plane that is at an angle of theta with the horizontal. A force of magnitude F at an angle theta with the plane is exerted on the block as shown above. Holy smokes, they're giving us another angle now. That's why this is a little different from the past ones. That's why this is a little harder, right? We started with the easiest ones. We're working up to the harder ones here. As the block moves up the plane, there is a frictional force. There is a frictional force between the box and the plane of magnitude F. What is the magnitude of the net force acting on the box? Holy smokes. This seems like a lot going on here. Now, you might be able to look at answers in multiple choice. You might be able to look at them and kind of figure it out. But let's see if we can talk through it real quick and make sure that we understand what's going on. First things first, this is my new axis, x and y. Okay, I do that because I want acceleration to be on one of my axes. I promise you guys, if you were to have to deal with a horizontal acceleration and a vertical acceleration, it greatly complicates this problem. In addition, most of our forces here are going to be right on the axes, which is nice. Okay, so what are the forces here? Well, we've got the force of gravity, which is straight down. Okay, this, of course, is theta. We've talked about that before. We've tilted our axis over theta degrees so that we can move it over there. So that is theta. We have this force right here, which is at an angle of that letter, phi. Now recognize that that angle is now the angle with respect to my x-axis, so that's actually really nice. We've got friction. It does say that there is friction. So friction is this way, just like that. And then we've got the normal force, which is up like that. Now, in this question, they wanted us to answer it with respect to variables that we've been given. So we can use the angles. We can use the mass m. So we've got m. we got the angles, we've got the force of magnitude F, and that looks like it. So whatever answer we get needs to, oh, and it gives me the frictional force between the box and the plane. So it gives me that F there. That's nice of them. And it asks for the magnitude of the net force acting on the box. So here we go. Let's figure it out. The net force acting on the box, we already know that the vertical forces are going to balance out, right? Those are going to balance out because it is only moving in the horizontal. That was the whole point to tilting our axis to the side, is because now we can ignore any of the vertical forces. All we have to worry about here are the horizontal forces. So I've got friction, which is down the ramp. And I'm just going to put in straight up negative friction. Friction is down the ramp. Done. Okay? Then I've got the horizontal part of gravity here, which is this guy right here. Now notice that is opposite the theta. So that's going to be Fg sine theta. All right? Now that, you'll notice, is to the left. So that's going to have the same direction as my friction there. So I'm going to put minus there. All right, normal force is perpendicular, so that's not important. And then we need the horizontal component here of the force that's being applied. So that is adjacent. So here's my right angle. That is adjacent to the phi there. And so we're going to go adjacent. So that will be plus F cosine. All right, so we've got all the forces there, all the horizontal forces. The friction, force of gravity, and the force due to the applied force. Now, we do have to be careful because it does ask, we can't have Fg here. We do need to put in the mass, and G, the small g is always allowed because that's a constant on the surface of Earth. So these are the net force. The vertical forces, they all cancel each other out. So all that I'll be left with here will be negative F, which is allowed, that's given in the question, minus mg sine theta, m is allowed, g is allowed, theta is allowed, plus f cosine, just like that. You'll notice f is there, and so is that. And therefore, that is the sum of the forces. That answers the question. We don't have to do anything else, no more solving, no rearranging. All it was they wanted you to take those horizontal forces, recognize that the vertical forces were not important, they were going to cancel out, and be able to use the correct trig to connect both the force of gravity and the applied force to our new horizontal on the slant. Okay? That's it. All right. Planet X has twice Earth's mass and 3 times Earth's radius. Magnitude of the gravitational field near planet X surface is most nearly. So again, we're going to try to compare, in this situation, we're going to try to compare planet X to Earth. So Earth has a gravitational field of g, right? The acceleration of gravity, 9.8 at the surface of Earth, right? In our formula packet, it doesn't give us a full equation for g, but it does tell us that g is equal to the force of gravity divided by m. And this m here is the mass of the object feeling the field. So if we have the force of gravity between Earth and an unknown mass, then we would divide by the unknown mass. And remember that Fg is equal to g m1 m2 over r squared. And so if I divide by the mass that is feeling the field, that would be this one right here. So all that's left then, when I divide by m, is that g, gravitational field anywhere, is going to be equal to g, mass of the object creating the field, divided by the distance from the center, squared. All right? So that's what we're going to look at. Now here it says planet X has twice Earth's mass. So I'm going to take this number and I'm going to double it. And it says 3 times Earth's radius, so I'm going to take this number and triple it. So what does doubling the mass do? Well, doubling the mass will double the field. So double the field here. If I triple the radius, Remember, that's on the bottom, so I'm going to divide by it. But it's also squared, so 1 over 3 or 3, if I do 3 squared, then I get 9. And so I'm going to need to divide by 9. And so once I do that, I can take my original G, the field of Earth, and then I can double it due to the mass, and then I can divide it by 9, or in other words, I'm going to essentially divide by 4.5. You can write this however you want, but essentially the answer should be 2G over 9. That would be equal to the gravitational field at the surface of planet X. All right? You can put RG in, 9.8, and then you'd get an actual value for that if you need to. All right? That's all there is to it. Just like that FG question that we did previously, this then allows us to calculate the field. Remember that field just takes out that second object. The field is the field being created by a single mass. All right? And let's go back and do another one. An object begins, An object begins at position x equals 0, moves one-dimensionally along the x-axis, so it's moving forward and backwards, with a velocity v expressed as a function of time according to the graph. At what time does the object pass through x equals 0 again? Okay, so I have a velocity versus time graph here. I do note that I'm starting at rest, and then I'm going away. It is very tempting to say that it comes back here at about 15. But all of this time, it has had a positive velocity, which means it's moving to the right the whole time. Now, when this goes up, it's speeding up. When it goes down, it's slowing down. But it's still going to the right that whole time. So I haven't returned yet. How do we get displacement from a velocity versus time graph? Well, hopefully you remember that it comes from the area under the graph. All right? So this would be a positive area. That would all be a positive displacement. And then this would all be a negative displacement. So what I really need to do is I need to figure out how far did it go to the right to figure out how far does it need to go to the left to come back. Now, you could do this by calculating the areas, right? You can take the triangles. You can find all those exact areas. I'm going to do it a little more geometrically here because I think I can do that and solve the problem a little bit quicker, right? I want you to think about different ways of approaching this. One, just calculate, you should be able to figure it out, okay? What I'm noticing here is that this triangle looks like it's about 5 by 20, and this triangle right here is also 5. It goes from about 15 to 20. It went from 10 to 15, 15 to 20, and also has a height of 20. So these two triangles are identical. They essentially cancel each other out, right? So what I'm left with here is this triangle. Okay, this triangle has a base of 10 and a height of 20. You can do this again logically if you want. You can just go 1/2 times 10 times 20, and I'd get 100. Okay, that means I need to go through 100 here. I don't want to go through another 10 because that would be 10. This would be a rectangle down here. So I actually only need that rectangle to have an area of 100. So the area is base times height. I already know that the height is 20. So I'm going to do base times 20. And when I divide by that, I get that I need my base to be 5. And so I need to go from 20 to 25. And that then would give me an area, half of a square, that is equivalent to half of that square right there, or a rectangle, however you want to look at it. So that right there tells me that I need to be at 25 seconds. The question is at what time? Well, the answer, my friends, is at 25 seconds. I have returned back to the place that I started. I went away, kept going away, stopped. Now I turn around. This cancels out that. This cancels out that. At 25 seconds, I am back to the location where I started. All right? Balls 1 and 2 are each thrown horizontally from the same height above level ground, but ball 2 has a greater initial velocity after leaving the thrower's hand. If air resistance is negligible, how do the accelerations of the balls and the times it takes them to hit the ground compare? Well, hopefully, I was actually surprised to see this one. This one bothered me just a little bit to see that this one was missed so often, because this one, they're both thrown horizontally. Once the ball leaves your hand, what are the forces acting on the ball? Just gravity. That is the only force. If that is the only force, then that is the only acceleration. The only acceleration would be gravity pulling the ball down. So what do we know about the accelerations of the balls? They are identical. Those balls will fall with exactly the same acceleration. The horizontal speed is independent of the vertical acceleration. Those two things have nothing to do with each other. And so therefore, we do not want to include those in our discussion. All right? Now, if the accelerations are the same, and the distance that they fall is the same, and they don't have any extra initial vertical velocity, then, well, y'all, the times are going to be the same too. This is the demo that we did in class. We had a ball that had 0 horizontal velocity and a ball that had a lot. And when I shot one and dropped the other at exactly the same time, we saw that they hit the ground at the same time. If that is the case, then it should mean that the time that it will take them is the same. The acceleration is the same, and the time is the same. The only things that should be different, the velocity when it hits the ground, right? One started with more energy, so therefore it will end with more energy. It will end with more velocity. In addition, the one that has some initial speed will travel a further distance, right? One is just going to go straight down. The other is going to go over that way and down, so it's going to travel a larger distance, all right? So these two things, however, should stay the same. A 100-kilogram cart goes around the inside of a vertical loop of a roller coaster. The radius of the loop is 3 meters, and the cart moves at a speed of 6 meters per second at the top. The force exerted by the track of the cart at the top of the loop is, we're going to find it. Now, a couple of things going through my head as I read this. The first thing is it's asking about a force. If it's asking about a force, there's a pretty good darn chance that I either need to calculate acceleration or I need to draw a free body diagram. So free body diagrams help me think about the situation anyway. And so I'm going to go ahead and draw my free body diagram. When I draw that, I'm going to say, well, there are 2 forces acting on the cart. Because it is under the track, then I've got the force of gravity pulling down, and then I also have the normal force of the track pushing down. Now, please don't freak out and say, then how is it staying up there? It's not. If it were not moving, what would happen to it? It would fall. The fact is, it's moving, so it should be following parabolic motion, but the curve of the track is getting in the way, and the track actually pushes it down even more. So as long as the track pushes it down faster than it would have got anyway, we know it's going to be okay. All right? Now, at this point, you should be able to say, well, it does give me a radius and a speed. That should make me be thinking about centripetal force, right? Centripetal force is mv squared over r. So at this point, I say, well, let's try that out. Can I do something with centripetal force? Well, I know that the centripetal force is the combination of the forces that are acting to cause the circular motion. Actually, if you remember a couple of questions ago, we said that when the object's going in a circle, all of the forces have to add up to give me the centripetal force. So let's do that. All of the forces must add together to give me the centripetal force. Now, we are assuming no friction here. If we had friction, we'd have to include that in there somehow as well, though the friction would be going exactly perpendicular to the centripetal force. But let's go ahead and we're going to assume no friction. Let's go with what we got. So centripetal force, we know, is mv squared over r. The normal force is actually what we're looking for, the force exerted by the track. So let's just go normal force there. And then plus the force of gravity, which is just mg. Now, with that, we actually have everything that we need, right? We've got the mass of the cart, which is 100 kilograms. We've got the velocity, which was 6 meters per second, so we'll go 6 squared. We've got the radius, which was 3 meters, and then we've got the normal force plus mass, which is 100, times gravity, which is 9.8. And so we should just be able to plug that right into our calculators, right? We're going to go 100 times 6 squared, and then we're going to divide that by 3. And with that number, they're going to subtract the 100 times the 9.8, and I get 220. So 220 is equal to the normal force. That's it, y'all. That's it. That's all you got to do. Anytime you got circular motion, it is a pretty good bet that you need to be asking yourself, what is the centripetal force? I'm going to set the centripetal force equal to the thing that is the centripetal force, whether it be a force or a combination of forces or a component of force. What is the centripetal force? Once you have that, you should be able to do some solving on both sides. Remember, centripetal force is mv squared over r. They only give you the centripetal acceleration in the notes packet, but of course force is acceleration times mass, and so you should always be able to deal with that as it is. Okay. All right, from there, all right, the horizontal wire shown on the right in the figure above will break when the tension in it exceeds the value T max. So this can go up to T max, and in that point it will break. What is the maximum mass that the hanging object can have without the horizontal wire breaking? Assume the wire on the left does not break prior to the horizontal wire breaking. All right? So all we need to do is we need to put our forces together. Again, I'm assuming that we want to write this question in terms of the variables given and constants. So T max is a horizontal force. All the other forces here, this is at rest. That's nice because if that's at rest, then the force of gravity will be equal to the tension, which means the tension of this right here will be equal to mg. This is the other tension in the string, which we'll just call T2, and that one we're going to need to break up into its horizontal and vertical components. Now, the part that's most important here is what's the maximum mass. We need to make sure that we are including that mass in our formula. So that mass is completely vertical, so I'm actually going to do the vertical forces first. Okay? So the vertical forces, I need the mass, the force of gravity pulling down. So that's going to be mg. And I'm going to make that negative since it's downward. And then I need the vertical component of T2. All right? So the vertical component, that would be opposite the theta. So that means I'm going to use sine. And so it's going to do plus T2 sine theta. Now I know that vertically it's going to be balanced until that instant when it breaks. So I'm looking at what is the maximum mass so that it stays the way it is before it breaks. So I'm going to look for this. All right. Now I have a couple of problems. Number one, this still has T2 in it. That is not one of the, I made that up. I made up T2, so I can't use that later. All right. The theta is okay. The theta is given in the question. The m is fine because that's actually what I'm trying to solve for. Everything else is okay, but I can't use that T2. So then I'm going to need to step in and say, well, all right, let's then connect it to the horizontal forces. So the horizontal forces, I've got T max, which is given to us, is to the right, and then I've got minus the horizontal component of T2, which would be T2 cosine of theta. And again, those two need to balance out if the string hasn't broken yet. All right? So if that's the case, then I will be able to solve for T2 here, right? And so I'm going to add that to the other side. And so I'm going to have T max equals T2 cosine of theta. I'm going to divide by the cosine of theta, and so I'll have T max over cosine of theta is equal to T2. Cosine of theta, theta is acceptable, so I don't need to do any inverse trig functions. That's just a number, right? I can do cosine of whatever the angle is, and I just divide by that number. So that's why I didn't have to do any inverse trig. Now this T2, I can take that, and I can put it back in, because that was the problem before, was I wasn't really supposed to have that T2 because I made that up. So now it's in terms of other things. I can go ahead and put that in. So if I put that in, then what I end up with is this. I will have negative mg plus T2, which is T max over cosine of theta, times sine of theta equals 0. Now, remember, the whole point of this is I'm supposed to be solving for the mass. What is the biggest mass that can happen? All right, so the biggest mass that can happen is the one that matches this T max, where everything, that T max is as big as it possibly can be. Anything larger than that, and it breaks. All right, so I need to solve for the mass here. So I'm going to do two things here. I'm going to move my mg over to the other side, and I know that sine divided by cosine is tangent. Sine over cosine is tangent. So I'm going to rewrite this as T max tangent of theta is equal to mg, because I added that to the other side. And then I'm just going to divide by g. So my final answer is going to be T max tangent theta over g is equal to the largest mass that that m can possibly have. All right? You got angles. You're probably going to end up doing both horizontal and vertical. Even if you're not sure what to do, if you see angles in there, it's a pretty good bet that you're going to want to write two different equations, one for the horizontals, one for the verticals, and work with them that way. Okay? Remember that in these situations, we do want to only use variables given to us in the question, which are T max, mass, and then of course the angle which has been given to us. And that's all that is all that we have here. Okay? So, good. Let's move on to another one. Just a few more left. Here we go. Objects 1 and 2 have masses m1 and m2 respectively, where m1 is less than m2. The objects are in outer space far away from any other objects, as shown above. Point P is located halfway between their centers. At what location, if any, is the gravitational field due to the two objects equal to 0? All right, now one of the things that you want to remember here is that field is a vector. Due to the fact that field is a vector, if we have field going in opposite directions, then you will add those together and get 0, right? Another thing to kind of think about is that if the field is 0, then the force will be 0. So if we can find a place in between the two where the force is 0, then we'll end up getting a field of 0. So at what location, if any, is the gravitational field equal to 0? Well, we know that this one is larger than this one. So this one's mass is larger than this one. Now, if this one's mass is larger than this one, then at this point P, the gravitational force, or the gravitational field, would be larger pulling in this direction compared to that one. Now, as we get closer to mass 1, obviously this force will get weaker and this one will get larger. And so as we move this direction, we can say somewhere between mass 1 and P, the field will be equal to 0 at that point. All right? We can't say anything more than that because we don't know how big M1 and M2 are. If we did, we could figure out, using our gravitational force or gravitational field equations, we could figure out exactly at what point that could happen. But for now, we will just say that somewhere between M1 and P, the field should be 0. We should be able to place an object that, because of the competing fields between the two objects that are here, there would not be any overall force. All right. Next up, a box is given a sudden push up a ramp. Friction between the box and the ramp is not negligible. Which of the following best describes the directions of the actual forces acting on the box as it moves upwards after the push? Okay, now obviously this was a multiple choice question, but let's just go ahead and talk about the direction of each of the forces that are in play. All right, so we do have a ramp. We have an object that is given a sudden push, so now it is sliding up the ramp. Please do recognize that the velocity is upwards, but it does say that it's just a sudden push, and then after that, as it moves upwards after the push, so the push isn't still on it, okay? So we should have just a couple of forces here. You should have the force of gravity, which would be directly downwards. The force of gravity is always directly downwards. You would have the normal force, which is perpendicular to the surface. It's also perpendicular to the direction of the motion. It is not directly opposite the force of gravity, okay, because the force of gravity is straight down, always straight down towards the center of the earth, whereas the normal force depends on the surface that is creating that force. Okay, lastly, if the velocity is up the ramp, then the force of friction should be down the ramp. Now, overall, we know that the net force will be down the ramp because the object will be slowing down as it comes upwards. Okay? After a long time, the box will reach the top and it will start moving down. As the box starts moving down, you will continue to have the normal force in this direction. You'll continue to have the force of gravity in this direction, but as it slides down, friction will then be in the opposite direction. Remember, friction is always going to oppose the motion. As long as it's sliding, then the friction should always oppose the motion, whatever direction that is. If it's at rest, then it will just oppose whatever forces are acting on it. For example, if it gets up to the top, and at the top it stops, why would it stop? Well, it would stop if the horizontal component of gravity here is not strong enough to oppose the static friction that it's having up at the top. If this is equal to that, then it won't start sliding down the ramp. And you've seen that a lot of times. You put something on a ramp and it just sits there on the ramp. That's because the static force of friction is equal to, it's opposing the force of gravity. If the force of gravity is larger than this, then it will start sliding, and instead of static friction, we will now have kinetic friction, just like that. Okay? So, fairly straightforward, thinking about the forces, just like that. Okay? Next up, the inclined plane in the figure above has two sections of equal length, section 1 and section 2. So these two are equal. Different roughness. The dashed line shows where section 1 ends and section 2 begins. A block of mass m is placed at different locations on the incline. The coefficients of static friction between the block and each section are mu s1 for section 1 and mu s2 for section 2. All right? It does say that mu s2 is greater than mu s1. So the friction in section 2 is greater than the friction in section 1, at least the static friction. It doesn't really give us, oh, there we go. Coefficients for kinetic friction are mu k for section 1 and 2 mu k for section 2. So again, the coefficient of friction is larger in section 2. If the block is at rest on section 1 of the incline, what is the magnitude of the force of static friction exerted on the block by the incline? So all that, and we actually don't need anything. We don't need anything at all from section 2. It is at rest on section 1. Now this is very similar to one of the other questions that we did. We'll go ahead and talk through it quickly, but I'm not going to take as much time on this because we've done a lot of these things on ramps already. So we look at the object on the ramp, If it is at rest at that point, we do have the force of gravity down. We have the normal force, which is perpendicular to the surface. And the reason why it's not going down, it says it's at rest in section 1. The reason why it's not going down is because of friction, which is opposing that horizontal component of gravity. So it's asking for the magnitude of the force of static friction exerted on the block. So if we want to find that magnitude, we could find that in a couple of different ways. One would be just saying that the force of the friction should equal mu k times the normal force. Unfortunately, the normal force we don't know, so the normal force would have to somehow be connected to the vertical part of gravity there. This is theta. It does give us an angle there. It gives us that angle theta. So theta, again, remember, is this angle right here, because we're going to take our axis which was vertical and horizontal. This is our new vertical and horizontal. So we've taken that axis, which was straight up and down, and we've rotated it over theta degrees, because that horizontal was horizontal. We've rotated it up so that it matches that theta right there. So this is theta. So for the normal force would have to balance the vertical part of gravity, right? That's the only other vertical force, and it's not accelerating vertically. It's only accelerating down the ramp, which is our horizontal axis. So therefore, we can go, that's the adjacent side. So the normal force would be Fg cosine of theta. So the friction could be, sorry, I said mu k, I do mean mu s1. Okay, from there we've got the force of friction. This should be okay. We're going to go ahead and put Fg in terms of mg. So we'll go friction equals mu s mg cosine theta. That allows me to do friction in terms of things that I have here, the mass m, the mu s1, right? Everything is in terms of things that are given to me in the question, with the exception of g, which is a universal constant. Now, that's one way to do it. Depending on what the answers are in the multiple choice, there may actually be an easier way to do this. In fact, we also know that friction must equal the horizontal component of gravity. The horizontal component, being the opposite side from that angle, would be simply mg sine theta. And maybe that's all we have to do. It just depends on what the answers are in our multiple choice question. As far as we're concerned, if this was free response, either one of those would be valid. And in fact, in many situations, you're probably going to be putting both of those together, setting them equal, and solving for something, right? This would allow you to somehow solve for theta if that was necessary, if you knew the coefficient of friction, right? So you can either look at the vertical forces, knowing that friction is equal to the coefficient times the normal force, or we can just straight up say, well, friction is equal to the force of gravity times sine of theta, because those horizontal forces have to be balanced. If I remember correctly, in this question, the answer was simply this. Because we're so used to going into this, that was actually not one of the answers down below. This was, because all they wanted you to do was recognize that the force of friction was equal to the horizontal component of gravity, and that's why the block was staying at rest. All right? Okay. Next question. We're getting into the most commonly missed questions now. These were missed by, I believe, everybody that attempted this question. So here we go. Two blocks of masses M and M are suspended as shown by strings of negligible mass. If a person holding the upper string lowers the blocks so they have a constant downward acceleration A, the tension in the string at point P is... And then here, they just want us to write a equation with variables, the variables that I have, m, and of course g, that will help me to find out what the tension there is. All right. They do also give us acceleration a, so we can use that as well. So we're allowed to use m, we're allowed to use the capital M, and we're allowed to use acceleration. Those are the only things that we're allowed. All right. So let's go at it. Probably the first thing that we would do is let's draw a free body diagram. So if I draw a free body diagram for mass m, I would have the tension, and then I would have just the mass, the force of gravity on the big mass there. And so possibly I would be able to get an equation straight from there, right? I could go tension minus the force of gravity on mass big M. That should equal mass, this is the big mass again, mass times acceleration. Now, it is going to be accelerating downward, right? And because of that, I am going to put a minus here, just like that. And so that'll allow me to solve for the answer. And so I should just move things around, and I'll go tension equals FGM, which would be mg minus ma. And so then I just have m of g minus a. I believe that a lot of people miss this question, probably because they did not put the minus here. Please recognize that they're saying that this is a constant downward acceleration of a. They are assuming that a is positive here. If it is downward, and I have designated FG as being negative because it is downward, then I need to make sure to represent that this is also downward. Okay? Let me show you what would happen if we did it a different way, right? If instead we were to say that down is positive, then we would do this. We'd say negative tension is plus Fg equals ma, just like that. Again, we would want to move the tension over and move the ma over, so I'm going to add tension to the other side, so that'll give me T here. I'm going to subtract ma to the other side, so I'm going to have Fg minus ma, and of course Fg is still mg minus ma equals T, and we end up getting, see, the same thing no matter how we do it. But you do have to be really careful with those signs anytime that you're dealing with anything that's a vector, a force, a momentum, a velocity, an acceleration, right? All of those things that are vectors, directions are going to be really, really important. All right, next one. Okay. A rope of negligible mass supports a block that weighs 30 newtons, as shown above. The braking strength of the rope is 50 newtons. The largest acceleration that can be given to the block by pulling up on it with the rope without breaking the rope is most nearly. All right. So this is I was actually surprised at how many people missed this one. Everybody that attempted this, at least 6 or 7 people, missed this question. Okay, please take the time to write out your Newton's second law. This is your free body diagram. You've got the weight, which is the force of gravity pulling down. You've got the tension, which is pulling up. At this point, you determine which is positive, which is negative. We add them all together. So we go sum of the forces equals ma. Sum of the forces, it is going to be pulled up. So I'm going to go ahead and call up positive. So I've got tension, which is upwards. I've got the weight, which is downwards. And that's going to be equal to mass times acceleration. Weight is the force of gravity. So remember, Fg equals mg. So if I want the mass, I'm going to have to take that weight of 30 newtons and divide it by 9.8. And so if I take 30 and divide it by 9.8, then I get 3.06. So 3.06 is the mass. The tension is going to be 50 because that is the breaking strength. So I can do up to 50 newtons of tension. Any more tension than that, and the string's going to break. So I'm going to find the limit here by actually putting 50 there. And so from that point, I just do 50 minus 30, and then I divide by that 3.06, and I get an answer of that my acceleration is 6.5 meters per second squared. There's your acceleration. All right. Be careful. Be careful. Remember, newtons is force, so that would be the mg. And then mass would always be the kilograms that you get from that. All right? All right, so now we're going to look at the last question. If you made it this far, congratulations. This was the most commonly missed question on the assessment. More people miss this than any other question in the gold game. Okay? Now, this question is actually, the crazy thing is there's actually two ways to work through it. Okay? Now, I'll be honest. When I worked through it the first time, I made a little mistake that threw off the whole. I didn't even get one of the multiple choice answers. I didn't even get anything that was available. So I'm not saying it's easy, but there are two ways to do it. And honestly, the way that I didn't expect was actually the way that was easier to do it. Okay, so what I'm going to do is I'm going to talk you through the process that I went through. And then I'll show you afterwards. I was like, you know what the heck? I'm going to see if I can do it the other way just to see what it looks like. And I found out that the other way was actually easier. So let's have a look. An object of mass m is attached to a spring on a frictionless inclined plane that makes an angle theta with the horizontal as shown above. So we've got the theta, we've got the inclined plane, the ramp. The object is released from rest with the spring in its unstretched position. Okay, so unstretched is right there. That's the unstretched position. All right. As the object moves on the plane, its displacement from unstretched position is x, so how far it's gone from that position. The object subsequently oscillates around an equilibrium position at a displacement x naught from the unstretched position of the spring. Okay, so what it's saying is that the equilibrium position, which let's just go ahead and call this the equilibrium position right here, is going to be, that is equilibrium right there, is going to be my x naught, right? Now from there, it's going to do x naught again because equilibrium position isn't enough to stop it. It's just going to keep going until it goes x naught again, and then at that point, it's going to stop, and then it's going to reverse and go back the other direction. All right? So the question is, what is the spring constant of the spring? Now, in doing that, we look at the equations that have the spring constant in them, and we've got F equals kx, okay, with the absolute value bars and vector symbols and all that. We've got the, that's the spring force. We've got the elastic potential energy, which is 1/2 kx squared. And then we have the period, which was 2 pi square root of m over k. Now, in looking at these, the first thing that I think is, well, I don't even have the period, right? I don't have the period. I don't have any information about acceleration, about the oscillation. I don't really know anything about any of that. So this one for sure, I'm like, definitely not. I'm not going to try that one. I don't have a graph, right? Sometimes the graph helps us get period. Lots of different things there. Nothing, I don't see any way that I'd be able to use period here. Okay, I'm looking at these two now. Originally, my thought was, well, if I used forces, I would need to do a free body diagram. I'd need to know more about the forces in order to be able to figure out what's happening at a specific location of time. I don't really know much about that, I guess with the exception of the equilibrium point, right? When I'm at the unstretched position, I might be able to do something with acceleration. I might be able to use something with the forces and determine acceleration, that kind of stuff, and I might be able to figure it out, right? And then I said, well, this is elastic potential energy. Elastic potential energy, well, that is a very clear, easy usage here because I'm starting at the top. At the top, I have gravitational potential energy. It's at rest, which means there's no kinetic energy. It's unstretched at the top, which means there's no elastic potential energy. At the top, it's pure gravitational potential energy. right? And then when it gets down to the bottom, what does it have? Well, when it gets down to the bottom, it's at the bottom, so there's no gravitational, right, between the block, earth, spring, right? There's no gravitational. There's no kinetic because as it gets to the bottom, it gets to rest, and then it starts going back the other direction. So there's no kinetic. All that it has is the fact that the spring is stretched out, and so therefore I have the elastic potential energy. So at the bottom, it's just US. And so my natural way of thinking is, well, it's oscillating. There's no outside forces. Energy is conserved. So therefore, I'm just going to go UG initial is equal to US final, right? That's what we just talked through. So UG initial would be MGH initial. That would be 1/2 KX squared final. I can actually get these things. They're not mysteries, right? I can get the height here. The height may be a little bit difficult. We do know that it's 2x naught, right? That's x naught and x naught. So this whole thing is 2x naught. Sorry, not x not to power 0, 2x naught. And I do have the angle here, which then should allow me to get the height. That's the opposite side. And so using trig, I'm not going to go through the trig. You should be comfortable with that by now. But using that, you should be able to get the h naught equals 2x naught sine theta because it's the opposite side, opposite over hypotenuse, right? And so I do know actually the initial height there. And so I can go mg, the initial height, which is 2x naught sine theta, which is then equal to 1/2 k, and then the x is how far it's been stretched when it gets to that final position. This is the one that actually initially caught me as I put x naught in there. But from here, it's 2x naught. And so we put 2x naught in there. And then we work through it, right? So at this point, we say, well, I can, this is squared, so I do need to square that. So I'm going to do the 2 squared, which is 4. And then if I half that, then I'm going to have 2. So I put all the constants together right there. I get 2k, and then I need to square the x naught as well. Don't forget to square the constant, okay? And then on this side, I've got mg2 x naught sine theta still. Now from here, I divide by 2. I cancel that out. I divide by 1 of the x naughts, which cancels that out. I'm still left with 1 more x naught, so I divide by that. And so all this is going to be over x naught. And I get my final answer, which is just that k is equal to mg sine theta over x naught. And that wasn't all that bad, right? It wasn't all that bad. All I had to do was use conservation of energy. I had to be careful with the height to use the trig. I had to square the distance, which was the 2x for how far the spring has been stretched. But all in all, it was just conservation of energy. Now, at that point, I said, well, what the heck? Let me try this again. If this is wrong, then I just don't do this in the video. But I wanted to say, okay, well, what if I did do forces? What if, again, this is my x naught, this is the equilibrium point, right? And I solve for something with the forces at the equilibrium point. Well, at the equilibrium, what forces do we have? We know this is a ramp, so we're going to tilt our axis just like this, okay? We've got the force of gravity, which is down. We've got the normal force, which is up. And then we got the force of the spring, which is that way. And what we notice is that we have the horizontal force of the spring, and we have the horizontal force of gravity. Those are the only 2 horizontal forces. So at equilibrium, the forces have to be balanced. And so my horizontal equation is just this. It's the force of the spring minus the force of gravity horizontal has to equal 0, because those are the only horizontal forces. They have to add up to 0 in order for it to be balanced. Well, the force of the spring is just kx, x naught, right, because it's gone x naught from the unstretched position, minus the force of gravity, which would be mg. Here's my theta, opposite the theta, so sine theta. And holy smokes, we add the mg sine theta to the other side. We have kx naught equals mg sine theta. We divide by x naught, and we get k equals mg sine theta over x naught. which is the same thing that we got previously, right? So 2 different ways to do this problem. As it turns out, the one that I thought was going to be harder, more complex, ends up being the easier way to do it. I make mistakes too, right? It's okay. We just try different things. Sometimes we say, maybe there's another way. But anyway, I wanted to show you that there's 2 different ways to do this question. Doesn't make it an easy question. Does not make it an easy question. However, it is still something that you can do in multiple ways. I hope that was helpful. I hope that the video in general was helpful, that you got a lot of information out of this, and I hope that you'll be able to use this to help you prepare for your AP exam. And we'll see you next time.